recording. Okay, good. So, welcome everybody. This is the second episode of our So You Want to Build the Humanoid Robot workshop. We're going to continue talking about humanoid robots, and in particular, last week we focused on the actuators, the servo motors and the different technology that you can use for implementing those. And today we'll look some more at how to actually construct the robot, in particular what technology is available for actually building the links of the robot. I have some of my students here again with me. We'll go by age, so our youngest member is Jill. Jill, if you can introduce yourself quickly to the audience.
Hi, I'm Jill.
And how old are you?
I'm 11.
11 years
12
old.
now.
12? Oh, I thought you looked more mature than 11. Nobody thinks that you're only 11 years old. Okay, and you go to school here?
Yeah.
Or you have a job? No
No.
job? Okay. And where you go to school?
Taipei.
Taipei? Okay, yeah, good.
Yeah.
Then you can introduce yourself quickly.
I'm Jared. I'm the first year master.
Mm-hmm. Yeah. And how much experience do you have with robots, humanoid robots? Have you worked with them before?
I have participated the FIRA competition
Okay, for how many years?
for 3 years.
Mm-hmm. Very good. And you used the Darwin OP robot.
Yes.
Okay. And which FIRA event did you work on?
I do the sprints.
Sprint. Okay. So what is the sprint?
The sprint is very difficult to finish. Yes.
But what does the robot have to do?
It should to work in a line and go forward and go back.
Yeah. So for the sprint event, as quickly as possible, the robot has to walk forward 3 meters and then backwards 3 meters. And it's one of the key events at the FIRA Eurocup competition. It's quite nice, quite exciting always, and it also shows how much the robots improve year by year. So when we started, it took 2 minutes to just walk 3 meters forward, and now it takes the robot 23 seconds to do forward and backwards. And teams are getting better and faster every year. Okay, next up.
I'm James Jung. Last time I explained my position.
Mm-hmm.
Yeah, I'm PhD student in ERC lab. I'm from South Korea, and I like humanoid robot.
Yes.
I have participated in intelligent humanoid robot competition during 11 years maybe.
Mm-hmm.
Yeah.
Also very successfully, his teams won many awards. And we also have Chrisman here. And
Hello, I am Jackie's student. I'm a second year master student, and I've also been working with robots for some time now.
mm-hmm. And where are you originally from?
I am Brazilian, yes.
Okay. Good.
Good.
Next up. You
Hi.
have to turn around. Yeah.
I'm Joe. I'm also second years of the master degree, and I start involved in robot when I came to ERC lab, so it's my second year for the robot experience.
And Joe also has other interests. He's actually a company boss. He has his own coffee shop. Yeah. And so do a lot of other students in my lab. Jill, for example, also likes to play the violin, right?
Yep. Like it.
Okay, then we better not have your mom watch the video. But you know how to play the violin.
Yeah.
Right? And Jasik and Chrisman and Jeff, they all like to do sports. I think they like to play basketball
Yes.
and are quite good at it. And so I think a lot of people have the wrong impression about people working with robots in the robotics lab. They have many other interests, not just sitting at home in the basement playing computer games and programming. Okay, so Jill, we'll start with you. You tell us what you did last week and what you're working on right now.
I did a home position last week, and I found out that I did it all right, so I had to do it again today.
Did it all wrong and now you have to redo it. Yes, that's okay. That happens to us a lot too. And why is the home position important?
Cause I'm not sure.
Okay, the home position for the servo motors is based on the fact that when we install the servo motors into the robot, then we attach the arm on top of the horn of the servo motor. And the problem is that the control that we send to the robot arm is based on degrees. So we tell the joint to move to 0 degrees or 90 degrees. But of course, if you think 90 degrees is forward like this on the shoulder joint, and you have the servo in this position, and now you attach the arm, then this will be 0 degrees, this will be 90 degrees. So the home position just establishes where we have 0 degrees so that we have a common reference point for all the control commands that we send to the actuators. So it's quite important to get that right. For humanoid robot, the shape that we usually have is like this for 0 degrees. A lot of robots use this position for 0 degrees. And Jill basically has to, in order to set the home position, we have to send 0 degrees to the servo motor, and then we have to attach the links at that position. And it's quite easy to get that wrong, and if you get that wrong, then your robot will lean to one side or the other and may not be able to walk or move in all the directions that you want it to go. So Jill will have to redo that today. So just do one servo, show how people how you set the home position. Sure.
You can see that.
Try and do it for the camera. Jill. Okay, so here's the servo motor. So now usually when you get the servo motor, you don't know what state it's in, right? So if you were to attach the joint at this angle, and oops, If you were to attach the joint at this position, and now you can send it to 0 degrees. So now Bill actually uses the microcontroller.
Good.
And now the link is pointing at about 45 degrees. But according to the instructions, it has to be 0 degrees. So we have to take the link off and then attach it at the right position, like this, yeah, and then tighten the screw. So now for 0 degrees, the joint, the servo motor and the link are agreeing in agreement on where 0 degrees is. And then we simply tighten the screw. So usually you only have to do that once during the construction of your robot. The 0 point should not drift as the robot gets older or as you're executing commands on it. Once your 0 degrees is set up correctly, unless you open that screw and remove the link from the servo, it should stay correct. It will stay correct. So there's no need to redo that. So we can tighten that screw now. Okay, good. Well done, Jill. And how many more do you have to do?
I 6.
6, okay. And how many motors does your robot actually have total?
I'm 15,
15, yeah.
or 16.
Probably 16.
Yeah, 16.
And what do they move? What do they actuate? How many do you have in the arm?
4. 4.
4 should be 3. 1, 2, 3.
2 arms,
Pardon?
like 2 arms or something.
1 arm.
3.
3, huh?
Yeah.
And in the legs then? 5.
Yeah. I think so.
That's a pretty common configuration. It means that the robot can move its hip like this and like this. Means that we have one joint in the knee, and the ankle can move up and down and also sway left and right. The joint, usually our robots usually have 6 joints in the leg, because we also have this degree of freedom in the hip, so that that it's easier for the robot to walk in a turn. But for simple robot design, it's actually not so important. I think for a light robot that walks in a straight line most of the time, that degree of freedom can be saved in order to reduce the cost. If we look at this one, Jeff, you can pick up this robot. You can show the degrees of freedom. The Bioloid has this extra joint. You can see it can actually move like this. So we have 1, 2, 3, 4, 5. Those are the same between Jill's little robot and the Bioloid. And now we have one extra degree of freedom here. And in the arms, we have 1, 2, 3 degrees of freedom. Again, if you build a Bioloid, if you build this kind of robot, of course, both of them you have to configure the 0 position. So before you tighten the screws on the links, the gray parts here, you have to make sure that the servo motor is set to 0 degrees and that it's in the right orientation when you tighten the screws. Once that's done, then the design, the construction doesn't need to be changed. Of course, if you replace the motor or something like that, then you have to redo setting the home position. Also, last time we talked a lot about the technology of the servo motors. We talked about the RC servos that Jill is using, small ones, and the intelligent servo modules. This one would be a Robotis AX12A and AX18A. JSig, you can pick up this robot. A slightly more modern design, but the same kinematics. So, actually, no, not the same kinematics. This one uses parallel kinematics. That's, if you don't know what parallel kinematics are, then you should re-watch our episode from last week where JSig introduced the parallel kinematics. What I want to show here is this uses the Robotis X series servo motors, which are more expensive but also more powerful and their latest generation of servo motors. But again, we have 3 degrees of freedom in the arms, which is pretty common. Here, because of the parallel kinematics, we have 2 motors in the top and 2 motors in the bottom, but no motor in the knee. So that allows us to increase the torque, reduce the weight at the knee joint, and it has some other advantages as well. In particular, for walking gait, we usually want to have the foot parallel to the ground, because otherwise, if we don't have that, the robot is going to stub its toes all the time. Like if you trying to land your foot and your foot is like this, and you hit the ground, then the robot will fall over most likely. So we actually have to have fairly tight control on the ankle joint here to make sure that we land the foot full on the ground. One of the really nice features of the parallel kinematics is that it's, because these 2 joints are, and these 2 links are parallel, that means it's impossible for the foot to ever rotate upwards or downwards. This will always guarantee to be parallel to these 2 servo motors. So we don't have to write any software to be able to make sure that the foot is parallel to the ground. That is an advantage if you want to only walk. If you need to do something else like wall climbing, where you actually need to have that degree of freedom, that will be impossible for this robot to do. So depends on what the application is for the robot, what you want the robot to do. But those are the 2 main designs, I think, nowadays. Like even our larger humanoid robots all follow the same kinematics. They all use the same layout of joints and links. For the larger one and the smaller one, the only difference is that we that we change the kind of motors that we use. We use more powerful motors and we have longer links in order to build a stronger way. Now, one thing that we didn't talk about last time was actually when you work with humanoid robots, especially if you use the cheaper motors, actually the motors, their reliability and their durability is not as high as you would like. I think with the Bioloid, when we use them in research projects, then they would get a lot of use, but we would have to replace about one servo motor per month. About that. I think this robot maybe a little bit less, but still, the servo motors for humanoid robot, the weight, we also always want to make them walk as fast as possible. There's a lot of wear and tear on the servo motor. So when you're considering building your robot, I think you want to overspec your motors a little bit to make sure that they don't wear out all the time. If you run the motor and you're over torquing it continuously, that's bad for your controller board. It will burn out eventually. If you have large impact shocks on the foot when the robot lands, that will break your gears very easily. And the same, so I think it's probably worthwhile to invest in at least metal gears, unless your robot is very light. Field robot, we don't have any experience with that one yet, so we don't know how long it will last. But Jill, I think in general, is very tough on her robots. I think she's breaking them quite often. She's a bit of a troublemaker that way. How about Brazil? How long do your robots last there? Your drones?
I think our robots in our lab there were actually quite old. I mean, we made them last a long time. Yeah. But yeah, it needs like constant care.
That's true too. Yes. Specifically, you'll lose screws.
Loose screws. We also had a lot of trouble, especially when you're doing like Euro Cup and then you go to the competition and it's like high stress for the robots because there are maybe like 10 different tasks and everybody wants to use the robot and then maybe the cables break or you have like bad contacts, so all the time you're like checking the connections.
And actually, quite often you think that the servo motor is broken, but it's actually just the communication cable.
Yes.
Those ones are, the connectors are not as good as they could be, I guess. I think the modern ones, actually this X series has one nice feature that I like, and because the not this.
cheap. Porsche.
Okay. Some of the X series, then they can run the cable out of the center of the horn, so the cable comes out in the middle of the horn. That means there's less wear and tear on the robot. Yeah, so you can show this one to the camera. Yeah, so you can see. So this is one of the nice features of the X series, that the
Going through the middle.
So it comes out in the center of the output shaft. So that means that if you compare it to a robot here, there's less wear and tear on the cables, and less chance that the cable will actually be sheared by being squeezed inside of the. There's less chance. If you look at this cable here and the arm moves around, then you can see it can actually end up shearing the cable by pinching it somewhere, or just pulling it out of the socket itself. Much less chance with the new X series servo. So this is kind of nice. And I said last time already, one of the big advantages for the intelligent servo motors is that you only have one cable chain you can daisy chain your servo motor. So here we only have one cable come out of the controller for the entire left arm. Jill's robot, she will need to have 3 cables that move into the controller board. So here, with the intelligent servo modules, we really only need 4 ports, 4 chains for the right arm, right foot, and left foot, and then the cable just moves along one cable all the way to the ankle. Rather than having all these cables, the ankle cables all need to be connected back in a star configuration to the main controller. That means, and you'll see if you build your own cabling a robot in this kind of star configuration is also quite tricky. You have to pay attention to a lot of detail there to make sure that the cables are not sheared or torn out of the socket while the robot is moving or falling or whatever your humanoid robot is doing. Okay, good. Then you can have people look at what she's doing, and then we want to talk a little bit about actually building the mechanical construction for the robot. So there's basically what you need is a 3D CAD program that allows you to make the different pieces of your robot, the links, the parts that go between the servo motors. And JSIG is just going to show you one very quickly, which is called Tinkercad. There's different options. There's some free options. There's some free to use options, and then there's some professional quality options that are actually quite expensive, like a SolidWorks or CATIA. Tinkercad is quite popular with people because it's free, it's online, you don't need to install anything, and for simple robot design it is probably sufficient. So JSIG is just going to show you a short introduction to Tinkercad.
Okay. At last workshop, I explained some design tools like Tinkercad, FreeCAD, Fusion 360, LibreCAD, and Blender, something like this. Jackie explained CATIA and AutoCAD, Inventor, SolidWorks are very expensive. So developer recommend a beginner about FreeCAD, like FreeCAD or Tinkercad. And Blender is not a CAD tool, but you can use Blender for animation. So if you
Actually, you can also use it for building things, but its primary design goal is computer graphics and animation.
So some people use FreeCAD or Tinkercad for design, and then they render using Blender.
Yep, they export into Blender in order to get nice graphics of the robot.
So actually we designed that robot using CATIA like this. So if you design Tinkercad or FreeCAD, you can design like this, and then and then you can add electrical design like OpenCR and Intel NUC or Google Edge TPU like this. You can download this file on the company website. Then today I will explain Tinkercad, but actually I didn't use this, but today I will try this with you guys. So if you enter Tinkercad website, you can see, okay, I will log out first. Oh, change browser. Okay. If you go to Tinkercad website, you can see like this. Okay, very slow. And then if you don't have your ID, you should join like this. But I have, so uh, I will sign in using Google. Okay. Internet is too bad.
I think our internet is slow because
Yeah,
of the
because-
streaming.
Yeah. Tinkercad support 3D design and circuit design. If you click circuit design, you can use Arduino on website. So, but today we will do design using Tinkercad. Okay, so create new design. 너무 인터넷이 느려가지고.
So I think Tinkercad is especially popular because of its tie-in with Arduino. The fact that you can use the same software to lay out PCBs and run simulations of the Arduino is quite powerful and quite nice, I think.
If you, what is this name? Wheel?
Mouse
Mouse wheel. If you click mouse wheel, you can move workspace like this, and then if you up a wheel, mouse wheel, zoom in and zoom out like this. Then if when you click right button, you can rotate workspace. Yep, this is how to use
navigation.
navigation. Yep, and if you click here, you can see basic shape, text and numbers, characters. Okay, I can show you. This is basic shape. You can draw box, cylinder, and sphere like this. Then if you enter text and number, you can see like this. So if you want, very slow. Yeah, you can add this text on workspace, and you can change distance like this. Then characters, hand and glass.
Yeah, those are unless you want to give your robot sunglasses in the design to make him look cool.
So Tinkercad support many things like this. So you can use Tinkercad's libraries like these. Then okay, I will go to basic shape. Delete this. Okay, today I will make some box with hole inside. So Because if you make your robot, your humanoid robot, you will use RC servo motor or smart servo motor. In this case, you have to make hole to connect frame to motor. So making hole on surface, this is very important. So today, okay, you can click box, then you can
We need
put
to use the other box, isn't it?
and you
that
can change solid
okay,
or
yeah.
hole like this. Okay, we need a solid first, so I change it a hole to solid. Then we can this, yeah, we can change distance. I want to make 100 millimeter. The unit is millimeter, so I want to make 100 millimeter and 30 millimeter. And the width is 3t, like this. So
So then people can see it will. It's sort of the kind of shape that you would use between servo motors.
and change 3t, then change 3t. 3t t mean thickness. So we usually use a t for thickness. And then if you want to make a hole, you should add cylinder, because cylinder is hole shape. Then we can change. I will make a 4 hole, like 3 millimeter. 3 millimeter. And
Yeah.
then you
It's like
drag
Yeah.
the solid and hole, and then you should, what is this, group. Then you can see making.
Now we have a hole.
So we should add one more cylinder. Can I copy and paste? Oh, okay.
Hard to use right now with the internet being so slow.
Okay. Okay, then can merge everything. Okay. And we can make hole like this. But okay, I'll try.
Position is slightly
Uh-huh.
off, but the idea is so people can see how you would do that. You can take the measurement, the dimensions, and then you can align the holes
No, but I don't know which one is.
if you want to. But that's okay.
Okay.
We leave it like that.
Okay.
So now what we're gonna do is we're gonna show you our secret project. Give a little introduction. We have a very ambitious project going on right now, and Basic is just gonna pick up the camera and then show you what we're actually working on.